Hi, this is Mr. Sakaguchi, and I want to talk to you guys about what we did in class today. This is one part of it in terms of using the wave equation, and I'm going to do some examples and do a rehash of the EM spectrum. So remember we talked about light and EM radiation in general has wave-like properties and behaves like a wave. So this includes visible light and the rest of the EM spectrum, which I'll show you in a little bit. It is energy that radiates from sources like the sun or some other power source. All EM radiation, regardless of whether it's visible or not, will move at the speed of light. Remember, wavelength is the distance between peaks, and frequency is the number of wave cycles per second. If you look here on this example figure below, we can see that wavelength is from peak to peak, and amplitude, which we really didn't talk about much in class, but it's just basically half of the height of the wave. We can see here when we increase the number of wave cycles, in this first one there were 2, but here we have 4. And notice how the frequency increases and the wavelength decreases. So it's that inverse property we talked about before. And here's another example where we have the same frequency as in B, but the amplitude is a little bit smaller. So you can see that we can add a lot of variety to waves and their properties. This is the EM spectrum. This is kind of a nicer version of what I'd given you guys on that handout. Notice that gamma rays is on one end. This is the highest energy part of the spectrum, and the radio is the lowest. If we look at this in terms of wavelength, notice that wavelength increases as we go from gamma to radio, but notice how the frequency increases in the opposite direction. Again, they're equal and opposite to each other. And notice how the blue and the violet represents the high energy end of the visible spectrum, and red, orange, and yellow represent the lower end of the spectrum. EM waves, remember this inverse relationship which we talked about before in terms of the wavelength and frequency. This is our wavelength equation, or wave equation, you can say. This is just, it's the same as the one I gave you, but it's just algebraically a little different. The idea here is nu times lambda gives you the speed of light. Remember, wavelengths need to be measured in meters before you can use this equation. This is because the speed of light is in meters per second. The frequency will either be measured in units hertz or seconds to the -1. And in this figure below, you'll notice that there are different units of measure that we use for different types of radiation. The only one that is new on here that we haven't talked about before is angstrom. I don't require you to know it, but just notice that different units of length are more appropriate depending upon what kind of radiation we're talking about. And you also saw that on the sheet that I gave you today as well. Okay, here's a light example. So here we have two waves. Which one would represent blue and which one would represent red? If we go back and we look at our visible spectrum, remember, blue should have a shorter wavelength than the red, and it should also have a higher frequency. So if we look at which one has a shorter wavelength and the higher frequency, it's the top figure. So we would expect this top one to be blue, and then the lower wave would be the red. And hopefully that makes sense if you think about it. Here's some example calculations. Let's say we're doing LASIK, and the laser we're using operates at a wavelength of 640 nanometers. What's the frequency? We can use our wave equation here. Remember, c is a constant. It's the speed of light. But remember, because we have 640 nanometers, we can't use it directly because it isn't in the same units as the speed of light. So what we'd have to do is dimensional analysis to convert this from nanometers to meters. And then once we have that, we can go ahead and we can solve for nu by taking the speed of light and dividing it by lambda, which would give us our frequency. Here's another example. Here we have an FM radio station, and we're broadcasting at this frequency. What is the wavelength? Again, we would use our wave equation, and again we would have our constant. And in this case, we'd have to convert megahertz to hertz in order to use this, otherwise we'd be off by 1,000,000. And then once we're done with that, we can go ahead and we can solve for lambda by dividing the speed of light by nu, and when we do that, we get 2.901 meters. And that is that. I'll be back with the part 2 later.